Last time we covered the basics of type systems, and today what we're going to do is we're going to apply this idea of type systems into our language that we've been building so far, the J language. But we'll do it in little bites. So let's start off with giving a type system for a language that's very similar to ours, but just a tiny bit simpler. So there will be values, there will be variables, and there will be single argument applications. So this is like the Lambda Calculus. Values will be either lambdas, or they will be primitives, or they will be constants. Primitives, we're just going to give a few examples, but they contain things like plus, minus, multiply, etc. We have constants, which would be like the bools, the numbers, etc. Okay. Then we're going to have types, which will be either what are called base types or functions that go from one type to another, where B are the base types. And we're not sure exactly what those are. Okay. Now what we're going to do is we're going to assume the existence of a function called big delta. And what big delta does is it takes a constant or a primitive, and it returns a type for it. For example, a rule might be that plus turns to number, 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 and another rule might be that true becomes bool, or that 5 becomes num. And so what we're doing here is we are building up a type system that is parameterized over what exactly the primitives are, what exactly the base, the constants are, and what exactly the base types are. So we can describe our theory for what this programming language does without having to explain in detail exactly what all of the various rules for constants and whatnot are. Okay, so this is our language. Now what we'll do is we'll write down the rules, the inference rules for it. Now before, in our simple example, we wrote down the following. We wrote down that our theory proves that E has type T. So we write this as proves that E has type T. Now, one of the first problems that we're going to face with this system is the presence of variables. So if I were to just show you a variable just sitting by itself, the variable x, and I were to say, what is the type of this? You won't be able to know because you won't know where that variable is bound. So because of that, we need to augment our rule to the following. We write down gamma proves that E has type T, where gamma, whoops, I wrote an F. Where gamma is either the empty environment or it is one gamma that we've extended with a mapping from a variable to a type. And so the idea here is that this gamma records what we think all the variables in the program, their types are. So traditionally this area is for writing hypotheses. So we're basically thinking of of variables as like hypotheses. So in the present, so for example, we might write something like this. We might say that if x is number and y is bool, then this proves that x has type number. And what we're saying is, if we assume that x is of type number and y is of type bool, then we can prove that x has type number. All right, so with that little notational thing out of the way, we've defined our language, we've set up what our inference rules are going to be talking about. These, by the way, are called type judgments. So typing judgment. Now let's write down the rules. So the first rule is quite straightforward, where we say that gamma proves that B has type T if delta of B equals T. Next, we say that gamma proves that P has type T if gamma proves that if delta says that P is of type T. The next rule is also straightforward. It says that gamma proves that X has type T if gamma says that X is of type T. So these are the most basic rules. They talk about constants, primitives, and variables. Now let's look at the next rule. The next rule is going to be the rule for applications. It says that gamma proves that what symbol should we use? Let's call this one 1E2 has type range. Actually, let's do TR for type range. Type range if gamma proves that E1 has type T domain arrow T range, and gamma proves that E2 has type T range. Sorry, T domain. T domain. So what we're saying here is we're saying that we can conclude that an application is well formed and returns the type range if we can prove that E1 is a function that goes from domain to range, and we can prove that the argument is actually of the type domain. Okay, so now this means that there's only one final rule that we need to write down. We've written down the rule for constants, for primitives, for variables, for applications. Now we need to write down the rule for lambdas. So we're going to say that gamma proves that lambda x e has type T domain arrow T range if gamma extended with a mapping from X to T domain proves that E, that's the body, has type T range. So, what we're doing here is we're saying, I don't actually know what X is going to be, but I'm going to assume that I'm given the proper thing, the domain. And if I assume that, then I'm going to go and inspect E and figure out what it actually is. Then what I can do is I can say, well, that this whole lambda now, it is going to return, it is a function that takes a domain and returns that range. Now, one thing that's really interesting about this is that when do we actually check that the argument is the right type? Notice that we check right here when we actually provide the argument. This is one of the interesting things about type systems. They allow us to verify the body of a function before it is called. So that means that you write a function and you haven't ever called it yet. We can figure out whether or not there might be a type error based on checking that body, assuming that the arguments were given correctly. So we're going to assume that the arguments are given right, and there still might be an error, and then later on we'll actually check to see if the arguments are given right. Okay, let's look at an example derivation of this, an example use. So suppose that we were interested in checking to see if, let's just go with something really, really simple. Let's say that we're going to have lambda x, and then we're going to have plus 1, and then we're going to call that function that comes back with x. Then we're going to close that parenthesis for there. Then we're going to call this function with 2. All right, so let's check that. So we start off with the environment being empty, and we want to check this. Now notice that it is an application. Okay, so let's just label these rules. This is going to be rule 1. Let's do A. Let's do A, B, C, D, and E. Right? So this is an application, so that means that we have to use rule D. And rule D says that first, you check to see if the function lambda x plus 1x is something that goes from domain to range. And then after that, we check to see if the argument is actually of the domain. Now notice that we can check that argument right now. I just a moment ago I said you do this and then that, but actually technically this form right here doesn't say what order anything happens in. Okay, so we're going to check 2, and we're going to see that, aha, yes, it is a number. And we'll use that because big delta of 2 equals number, and that is rule A, I believe. A? Yeah, it's A. All right. Now this rule right here, we are going to check and see if it goes from number to something. Okay. So we're going to see if the empty environment extended with a mapping from x to number proves that plus 1x is something. Well, that right there is an application. So we're going to do another application. So now we're going to check to see. I'm going to write this a little bit simpler. I'm going to just say x is num. If that proves that plus 1 is a function, and x is num has to prove that x is something. And of course, this is going to prove that it's a number, and that's by rule, that's because x of number, x equals number, and that's rule C. Now this over here has to expect a number and return something. And that is itself another application. So we have to see if x number proves that plus is a function. And we have to prove that x num proves that 1 is something, which via rule A, we know that it's a number because big delta of 1 equals number. Then we have number here, and then we look and we see what plus returns. So plus, if we look at gamma of plus, big delta of plus, then we get number, arrow, number, arrow, number. So that means that this right here is number, arrow, number. This right here is number, arrow, number. This right here is then just number. Just number. And so that means that this is number, and this is number. So thus we've been able to construct a tree that shows us that this expression right here won't result in an error, and if it finishes, will return a number. We know that because that's what the progress and preservation theorems say. The progress theorem says that this will continue running without having an error, and preservation says if it returns, then it will return a number. All right, so we constructed this thing right here by hand. Let's write a function that does the same thing. So we're a function called type of, and it's going to take a gamma it's going to take an expression, and it's going to return a type. So when we call type of, and we're given some gamma, and we're given a constant, b, then we're just going to call the big delta function. If we call type of, and we're given a primitive, then we're just going to call the big delta function. If we call type of, and we're given a variable, x, then we're going to inspect gamma. All right. Next, if we call type of, and we're given an application of E1 to E2, then what we're going to do is we're going to say, actually, sorry, let me just make a little tweak. It's not that we return a type, it's that we maybe return a type. The reason it's a maybe is because sometimes we there's no actual type for something because we can't derive one. So what we'll do here is that the first thing that we're going to do is we're going to say let's assume that we're going to get back an arrow. Actually, let's not say arrow. That's like what it looks like. Let's call it a name. Let's say that we're going to say that a function that goes from t domain and t range comes back from calling type of with gamma and E1. And then we're going to have tx comes back from calling type of gamma E2. And then what we're going to do is we're going to say if t domain equals tx, then we're going to return t range. Otherwise, we're going to error, basically, and return nothing. Actually, let's just say that. Let's just say that we'll return, it'll be nothing. Because nothing means that it didn't work. Finally, we're going to say type of gamma, and we're going to get a lambda that has an x and an e. All right, now what do we need to do here? Essentially what we need to do is we need to return a function that goes from t domain to t range, where t range is the result of calling type of. So let's do it let's write it a little bit differently. Let's emphasize what order everything happens in. The first thing that we're going to do is we're going to say t range is the result of calling type of gamma extended with a mapping from x to t domain and e. And then we're going to return a function that goes from t domain to t range. All right. Now, this last thing that we wrote has a really big problem. And that really big problem is that this variable right here is unbound. Where in the program do we define what t-domain should be? We don't actually know, we know what gamma is right here because it's one of our arguments. We know what x is because it's one of the arguments. We know what e is because it's one of the arguments. But we don't know what t-domain is. We'll know what t-range is after type of returns, but we can't know that until t-domain comes back to us. Now, one thing that we could do is we could non-deterministically guess. So what we could do is we could say, I'm going to guess that it's number, and then try that. And then if that doesn't work, guess that it's bool, and we'll try that. Now the question is, how many guesses do we have to make before we find the right thing? The answer is that there's no number of guesses that could possibly work. First of all, our type system has an infinite number of types. because we can keep adding more arrows. So we could have a number, or number, arrow, number, or we could have number, arrow, number, or number, arrow, number, arrow, number, arrow, number, arrow, number. So we could have 4. Okay, we'd have an arbitrary number of them. And imagine that the reason that when we try number, it doesn't work. So that's why we try the next thing. But maybe the reason that it didn't work is because actually nothing's going to work. This thing is ill-typed because maybe it tries to call the function. It tries to treat 1 as a function and call it, and that doesn't work. So there's no number of guesses that we could possibly make. So that means that this function right here doesn't make sense the way that we wrote it. And if we tried to guess, then we would have something that was not decidable, only something that was recognizable, that was a recognizer. So that's a problem. So what we do instead is we have to go back to the drawing board. So what we need to do is we need to change it so that our language no longer says that that's what a lambda is. Instead, we have to make it so that our lambda notation explicitly says what the type of the domain is. And if it explicitly says what the type of the domain is, then at this point, we can then change the rule. So it says gamma proves that lambda x te has type, let's call it td here, td arrow tr, if when we assume that x has type td, then e has type tr. And we have to change the corresponding rule in our function to say that type of gamma lam x td, actually t domain e, it is equal to t range comes from calling type of gamma extended with x goes to t domain. Now it's bound because it's part of this data structure, e, and then we return a function that goes from t domain to t range. All right? This is an example, this thing right here, and this is an example of a type tax. It's something that we wrote in our program that is not useful. It's not part of what controls the computational behavior of our program. It's not strictly necessary because our programs worked just fine before we added this. Instead, we now have to add these to satisfy the type system, because otherwise it would not be decidable for the type system to figure out what this value was. There are many examples of type taxes in programming languages that use type systems, and people tend to really dislike them. And it's one of the reasons that people often say that they don't want to use type systems. Now, let me just make a little bit of comment about that. People have tried to run studies where they look at Java code and they look at C code that does the same thing, or Python code that does the same thing, and try to quantify the amount of extra types that are in a language. And people come up with numbers like, 10% of a Java program is types, or something like that. It's very hard to really quantify this. But very clearly, type taxes exist. Now, sometimes type taxes are useful because we've now written this down, and then we can publish this information so that people can automatically look at documentation. So calling it a type tax is maybe a little bit unfair because it is useful, but it's clear that we added it because the type system found it useful, was essential, as opposed to something that we wanted independently. All right, so this language that we've built so far is very simple. It only has single argument applications. Well, you can imagine how we could add more, so we're not going to really do that. And it just has lambda. So it's basically like the Lambda Calculus. Now, I'm not going to do a rigorous proof of this. But let's just look at what happens when we try to write a Lambda Calculus term that runs forever. So recall that in the untyped lambda calculus, that's the normal one that I showed before, we could write the following function, lambda x xx applied to lambda x xx. This is the so-called omega term. What happens is we take this value right here, it gets plugged into there, which then gets substituted for these two places, so we get lambda x xx, that's this thing in that spot, applied to lambda x xx, that's this thing in that spot, and as you can see that these are identical. So that means that omega reduces to omega, therefore it continues running forever. Let's look at what would happen if we tried to write this in a typed way. We would have to write lambda x is of type t, for some type, we're not sure what it is, xx, applied to lambda x, let's just call this p, xx, because they're not necessarily the same type. Okay, so now let's try to use our type system to write a type for this. So we're going to start off with gamma is being empty. Let me just move this a little bit. So gamma is empty, and we have to prove that this has some type. Okay, actually let's not use, okay, so this is an application. So because it's an application, we want to prove that lambda x t xx is a function, okay, and it's a function that's going to take in whatever this thing is, okay. But now the function is definitely going to be taking a t, because that's what we wrote down right there, okay. And over here, we're going to say that this function over here, p xx, it's going to take in, it's going to take in a p and return something. All right, now let's open up this and see what happens inside here. We're going to say that x is of type t, and now we have to show that that x of x returns whatever that is. So let's just call that q. Okay, so it's got to return q. So that means that what we need to do is we need to prove that x t, okay, has some type, but it's got to be a function. So it's got to be a function that takes in, let's use the symbol s, goes to q, because we know that that's the return type q. And then we know that it does that if t equals s arrow q. All right, but then come over here, we've got to also show that x has type s because it's the argument. Therefore, we've got to make it so that t equals s. So now we have to ask the question, is there an s such that s equals s arrow q? Well, the only thing that could have that type would be if s were an arrow. So that means it would have s1 arrow s2 would equal s1 arrow s2 arrow q. Okay, well that means that s1 would have to equal s1 arrow s2, and s2 would equal q. So now we have to find an s1 such that s1 equals s1 arrow s2. This is a very informal way of saying it, but essentially what happens is that such a type cannot exist because it would be infinitely large, and there are no such infinitely large objects in our language. So we cannot type this program. This is an example of how there are correct programs that have no errors, like gamma, but they are not inside of the type system. So the type system refuses to allow them. It turns out that this type system that I've written down right here does not allow any recursive functions at all. So there's no recursive function that you can write that works. So because of that, although recursive functions were built in to the untyped lambda calculus without any special provision via the omega operator, the z combinator, and so on, in our typed version of it, we have to explicitly add them back in ourselves. So what we can do is we can add them in by changing the rule again. So we'll say that it's no longer the case that you write x is of type TE. Okay, we're not going to do that anymore. We're now going to say that a lambda is going to be f, where we have x of TE. And now this f right here is going to be the recursive name. And so we have to write down the type rule that says that gamma proves that lambda f xt e is of type t, let's call it td, td arrow tr, if we assume that x is of type td, and we assume that f is of type td arrow tr, and this proves, and you have to use these assumptions to prove that e has type tr. Now, unfortunately, there's a problem with this. And that problem is that this tr right here is not determined from the input. So it is the input to this judgment, but it's not in the input of this one. So that actually tells us that we can't use this either. What we have to do is we have to say that instead lambdas have to say that they return a tr, they have a function name, and they take in an argument x of type td. And so once we change it in that way, so we have lambda tr f x of td, now we have enough information in the type. This now says that we have two type taxes. So we have two examples of a type tax in our language where we have to explicitly say what the argument is, and we have to explicitly say what the return is so that the function can be used recursively. In addition to that, simply having this in the type system period is a form of a type tax, because by using the type system, we make it so that programs that we want to use, like recursive functions, are no longer acceptable. So we have to make our type system more complicated to admit those kinds of programs. It turns out that almost all of the ideas that we had before about how to add features to our programming language directly in the standard library require a more complicated type system. For example, let's talk about booleans and if statements. So we previously defined true as being lambda x, lambda f x, and false as lambda x, lambda y, y, and then if as being lambda c, lambda x, lambda y, c x applied to y. Now, the problem with this is that it is difficult to determine what the return types of these things should be, because true could be, like, essentially, when we have a function call, we don't want to have a function call mandate that, when we have an if statement, we don't want all if statements to always take in numbers. We want them to sometimes be numbers, sometimes be bools. We want them to sometimes be functions. Basically, the types that we would have to put on these, we'd have to annotate these with would be too strict. Now, eventually we'll talk about how to support anything with a system called polymorphism. But the simplest thing to do is to mandate that true, false, and if are integrated into our language. So we have to, the simplest form of the type system is to say that we expand our expressions to include ifs. And once we expand them, then we have to make a type rule. And so the type rule is going to say, if EC, ET, EF has some type, if gamma proves that EC is a bool, gamma proves that ET has a type, and gamma proves that EF has a type. Now the question is, what should go in these boxes right here? What are some different ideas that we could have? One thing that we could do is we could write T1, T2. Okay, so they each have some type. But now what goes here? What if we wrote T1? Would that be correct? Let's look at an example. That would mean that we could write +1 if false 2, 2. What this program does is there's an if statement that evaluates the false side that gets the string 2. But this type system would say it's okay because this type right here is supposed to be number and the true branch is actually number. So T1 isn't the right thing. What if we wrote T2? Is that the right thing? Well, no, obviously we can write a program that has the opposite problem. So that's not right. Okay, so if it's not T1 and if it's not T2, maybe we could imagine that our type system is more complicated. Maybe we could do something like, say, T1 intersect T2. The idea is that it returns something that is the combination of both T1 and T2. So in this case, it would be number intersected with string, and number intersected with string is nothing. And since it's nothing, then you can't add it. So that makes sense. So this program would have an error in it. And if they happen to both be the same thing, they both were number, well, when you intersect them together, you just get the thing, so it's just number. Another idea is you could say that somehow it returns both of them. It returns like T1 union T2. The idea there is that right here we're saying, well, this thing returns a number or a string, and you don't know what it's going to return, therefore you can't add it because you can't add necessarily to this. So these systems with an intersection and a union both exist in the literature, but they're considerably more complicated. And let me just comment briefly about how the union system would work. The union system is implemented by typed racket. That's a notable place that implements it. And the key problem with the union system is that if this thing returns a number or a string, then how do you actually consume a number or a string? How do you know what to do with it? Essentially, we have to complicate the rest of the system with a way to take an x union y and figure out if it's an x or if it's a y. And there's a way to do that. It's called occurrence typing, but it's very complicated. So occurrence typing. So if you're interested in this, then I suggest looking into it. However, we're not going to do either of those things. Instead, what we're going to do is we're not going to have these be independent things T1 and T2. We're just going to say that they actually have to be exactly the same. And by making them exactly the same, now we avoid this complexity. Now, this is, of course, an example of a type tax, because there are programs that are totally fine that no longer work. Let me write a little example. Let's write a program that's called that says let x equals if less than read 5, then 2 else 2. So x now sometimes returns a number and sometimes returns a string. Now our program says if x is a string, then return the length of x, otherwise return x times 4. This program right here always returns a number. However, the rule that we've set up does not allow this program because it says that it's not okay for this to be number and that to be string. It insists that they're the same. We know that this program is correct because it checks to make sure that x is a string before doing the string, let's call it string length, before doing the string length operation. And it knows that if it's not a string, it must be a number, so then it's allowed to multiply them. This is the sort of program that typed racket allows. Typed racket allows. And in practice, people write programs like this all the time in Python, JavaScript, Ruby, PHP, and so on. People write programs like this a lot. And all programs like this are an example of the sort of thing that are correct programs, but they're not typed. Now, saying they're not typed is a little bit specious because they are inside of typed racket. So there's this typed racket thing, which includes this program, but a simpler type system, like the one on this page, doesn't include it. Okay? So essentially what this tells us is that because we know that there's a gap between correct and typed, we can make more and more complicated type systems, adding features, just like we added recursion right here, just like we added recursion to support recursive functions. Now we've added this rule to support if statements. Now we can make the typed racket system in occurrence typing to support this program, and we can keep making type systems more and more complicated until we get the features that we want. And we can keep doing that over and over and over again. And it would totally be possible to do that. And in fact, this is what I've just said essentially describes the entire industry of programming language theory, where people work on more and more complicated type systems to address more and more complicated pieces of traditional programming. So that's enough for today. We'll add a few more features next time, and see you then.